Now let's look at another connection, which is column to column connection. And as the name says, you can see here, column to column splices are made either by bolting mechanical connectors or anchored into the separate precast components, or by the continuity of reinforcement through a grouted joint. So this is the most important thing. So what we are trying to see here is, we are ensuring the continuity of the reinforcement through, basically this is like a lap connection in a cast in place system. Is concrete. So you see here, there is a precast column and there is a precast beam. This is again precast column. So what we do here is, we create a tube, sleeve tube, and adjacent to the sleeve tube, you will also have the rebar of the column that will be there. Now from the bottom, the rebar will go inside to that sleeve, and then it will be grouted through this holes that are there. So that's what we say, the double bar from the corbel. And what we do here is, this is an in situ joint. So this is what you see here is actually an in situ joint. That means this region will be cast after the elements are kept in place. So this is your cast in place concrete, CIP, cast in place concrete, right? Now you can see here, in multiple ways we can look at it. For example, the rebar from here, it comes and then goes into the U. Similarly, the rebar from here, it goes and then like a U, so with the proper development length. Now the bars have to be continuous. Now the bars have to be go through the joint into the top column that it is coming. So now in the top column, how will it go into the top column? You need to have a sleeve that will accommodate. So here the elements have to be cast with precision, so that the bar from the bottom column can go into the top column. So that is very important. The precision of casting the precast elements are very essential when you are going for a grouted double joint. Okay, so this is the picture that what we are seeing here. So you can see here, this is your bars that are protruding from your bottom column. Now you create that hole through that sleeve, right? This sleeve or a coupler, and that will have a cap. The cap can be removed. Now adjacent to that sleeve, you will also have the rebar from this column. Then only the lapping will be achieved, right? So then like this, we snug it in, and then we do the grouting. For example, what you see here, there will be a hole like this, so through which you can actually grout cementitious material, and you can achieve through bond the transfer of force. This is again similar to the lapped joint that what we have in cast in place construction. Now another type of column to beam connection is dry pinned corbel connection. So why do we say this is a dry pinned? Is basically it's a pin connection, so that means no moment transfer. No moment transfer. It's a simple shear connection only. So you see here, I have a double bar that it is coming from the corbel. Now that has to go inside this beam, right? So that's what we see here. Okay. Now I put a double tube while making this precast beam, and then the double bar will go through the tube. Once everything is in place, what I do is I do some minimum grouting, very minimum grouting. Okay, that's why it's called dry pinned joint. So we do only minimum grouting in this double tube, but it's the quantity of the grouting is going to be very less. So through which I can ensure the continuity between the beam and the corbel, so that the beam cannot move away from the corbel and fall off, right? So this kind of connection ensures that it is not going to move away from the corbel. Now this is again a wet fixed connection. As the name says, it allows for moment transfer. That's why it's called as fixed connection. Now why do we call this as a wet connection? You see here, now this portion, the gray portion that what we have here is basically, this portion is actually a cast in place concrete, right. This will be cast in place, right. Now you see here the column to column connection, like what we discussed, through double tubes, sleeves that it goes through, the bottom bar goes into that dowel, that remains as it is. Now what we are also doing here is, there is projecting bars from the beams. For example, this beam, if you look at it, it comes like this and then joins, right. Similarly, from the other beam, if you look at it, it goes like this and then joins here. So there is a lapping for the bottom rebars also. In addition to that, now all these top bars that is required to achieve the negative moment capacity in the joint region. So this is a continuous bar, beam top. So that we are going to put it while we do the cast in place concrete. So in this way, I can basically, this is like your regular cast in place construction. This type of joint is also sometimes called as an emulative joint. Why it is called emulative joint is because we are trying to emulate what we try to achieve in a reinforced concrete cast in place construction, because the top, everything is cast together, then the top bar is continuous, so that it helps in transferring the negative moment that is developed at the support. So in the same way, the top bar here will help me in transferring the hogging moment or the negative moment, that typically what we say in the support region, right. So this is the way that the connection between column and beam is done. So this becomes like a fixed or a rigid joint, which helps in transferring both shear and moment. Now the next connection is again a simple connection, which is a dry pinned corbel connection. As the name says, you have a corbel, that you have here corbel, and you have the precast element that it is coming, and we don't want this precast element to slip away from the corbel. So what we do is, we put this dowel from the corbel encased into the hole that is provided in the precast element. Then we go ahead and do the grouting. Grouting is done later, same way. And but this dowel bar helps me in transferring only the shear, and it is not going to help me in transferring the moment. So that is why it's called as a pinned connection, right. Only the shear is transferred, but not the moment. The next connection is a dry fixed connection. You can see here, this is a dry fixed connection. So as you can see here, you have this column that it is going, and then I have simple corbel, and the beam is connected through this simple dowel bar just to keep it in place, because while you erect it, immediately you do this to achieve that it's not going to move away from each other. Then what we do is, we provide a continuous bar in the topping. For example, this is a topping bar. That bar also goes through this hole which is kept, this is a hole in column. So the bar will go through the holes in the column, and in addition to that, I am also going to have some cast in place concrete that is provided on the sides. But in the joint, the cast in place topping slab is not coming. It's just a topping slab that it is coming, but the reinforcement actually goes through the hole in the column, right. So you put some minimum reinforcement in the cast in place topping slab, and then you achieve the connection. But for example, if this bar, actually it is going only through the hole that it is provided in the column itself. Now you can see beam to slab connection. So again, this is a type 1 connection without the topping slab. So for example, you see here, this is a precast beam, and then while the casting itself, you create this kind of a U bar which you kept left open like this, right. Then what we do is, from the slab, precast slab, again what we can do is, we can create this kind of a hairpin kind of bars coming out, protruding out from each element like this, and then they lap like this. Then I can run some additional bars like this, and which is running perpendicular to the plane that what we are looking at, and then you put this in situ cast in place concrete here, then you fill it up. So, in this way I can achieve the connection between beam to slab, and now if I have adequate anchorage lengths, then this moment, this location can also transfer the moment. So, that is the idea, right. Right. So, now next let us look at the next connection, which is beam to slab connection. This is called a type 2 connection. So, here what we are going to achieve is, this is just the whatever the bar that it is coming, the screed bars that are coming from the beam, basically we bend it like this, right. So, these are some extra bar that you bend it to ensure some connectivity. Now, whatever the reinforcement that I require, I am going to put it only in this cast in place slabs, okay. 2 layers or 1 layer, whatever the number of layers, depending upon the thickness of your topping slab, you can provide a reinforcement. This is why we call this as type 2 is, here I am having a topping slab, okay, through the joint also. In the previous case, if you look at it, there is no topping slab. So, that is why it is called as type 1 connection. Then when you look at the next one, type 2 connection, you have a topping slab, right. So, in this way the beam to slab connections, 2 types of connections are possible. In addition to that, we can also have like this, for example, wall to slab connection again like this. I leave open this region, but the bars will be basically it will be coming and then it will be protruding. In addition to that, I can put some additional bars like this. In addition to that, the screed bar from the wall, this is wall to slab connection, right. So, you can take like this and put it like this. There will be a cutout in the slab for connection. So, this is your cutout that what we are talking about. So, there is a region, we do not create the entire element, we create some kind of a small projections. That projection is where we put additional steel, and then we do the in situ concreting, right. So, this is again wall to slab connection for type 1. Now, we can also have another connection, which is basically you can see here wall to slab connection, which is type 2 connection, and you can see that the bar that comes and then you bend it up here. These are basically screed bars from the wall. Then you have this precast slab that it is here. Now, I create again in situ topping slab. So, that is why it is called type 2. So, whenever you have a topping slab, that type of connection is called type 2 connection. When you do not have a topping slab, only with a little bit of cast in place concreting, if you do, that is called type 1 connection. These are the 2 common ways that wall to slab connections are usually achieved. Now, slab to slab connections, how the individual slab elements can be connected to each other. This is how you see here. This is a picture that it is clearly showing. At the bottom, you have these walls, okay. Now, this is one slab, this is another slab, right, and you can see the multiple slabs. You have these screed bars that are coming from the beam, and then what we do is an in situ topping slab that is done. So, these are precast slab, right. So, what we do is the individual precast slabs are connected by typically a topping slab. The topping slab also will have these nominal reinforcement. Usually the the topping slab should also satisfy some minimum thickness to achieve the diaphragm action from the seismic performance point of view. Okay, you see here now from slab to slab, if you look at in the plan, so you are going to have this lapping that will be happening at these edges. For example, these 2 precast slabs that you have, then I provide these in situ grout or concreting, and then the bars will be spliced like this. Okay. So, this is what we do. So, 2 elements, you will have a projecting bars. The projecting bars have to be connected with additional bars, and then they will be grouted together. Now, this length you have to calculate it, and you typically use high strength concrete or high strength cementitious grout, so that with less length we can also develop the strength required in this connection. Okay, so this is again wall to wall connection. You have typically 2 types of connections or joints that we call between wall to wall. you have a horizontal joint and you have a vertical joint. Typically, if you see here, this what you see here is a vertical joint. So, what you see here is a vertical joint, right. So, this vertical precast wall joints are actually they connect adjacent wall panels side by side, while horizontal joints they connect the panels stacked vertically, right. So, typically at different floors. Now, what is the role of horizontal joint? Horizontal joints they help primarily to transfer the vertical loads from the wall above to the wall below, right. So, only the help in transferring the vertical load. But vertical joints are the ones they connect the panels in the plane of the wall, and it provides overall stability and transferring the loads laterally. Okay. So, if you want multiple panels to act as a one single shear wall, the vertical joint has to be designed in a very critical manner. Now, let us look at it. So, you see here the influence of the vertical joint. If you want a rigid, you can have either you can create a rigid monolithic cantilever action, or with multiple, you can create multiple cantilevers which will be more flexible and this will be more rigid. If you have, let us say, a single wall panels which goes from 3 to 4 stories, then this is going to act more like a rigid monolithic cantilever connection. Then when you have multiple single walls are connected on top of each other in a vertical fashion, then it is going to more act in a flexible way and is going to act like a multi-cantilever system. And these are some of the pictures of the basement connections, and you can see here again, these are all the bars that you see here are all dowel bars that are sticking out, and the element will come and then it will be jointed through grouting. And you can see the lifting of one of the basement walls that you see here. Now, this is what we see here. These are all some of the bar that what you are sticking. These are your screed bars, and they will be bent and connected to the horizontal elements, and these are your main dowel bars. Okay. Sometimes the interconnecting the joints have to be done using cast in place concrete, okay, and you have to do it carefully, and so that there are not going to be any gaps, voids that will further lead to seepage or leakage issues. So, this has to be done in a very careful way, and you can all see this holes which are basically these are all grouting holes. So, through which basically grout you can see when you pour it, it comes out. Okay. So, in the precast from seismic resistance point of view or from lateral load resistance point of view, we can have different types of systems that can be designed. One is a moment resting fixed frames that we are very commonly we are aware of it. Another one is a shear wall based system. Then I can also combine both the moment resting frame and the shear wall to achieve a dual system. Now, what you see here is a moment resting frame connections, and here is a wall type connection. Now, I can also combine these to achieve the lateral load resistance depending upon the demand that what we have. For example, you see here this is a typical action of a frame, moment resting frame under lateral load. For example, this is a lateral load that is coming from, let us say, wind, right. So, the frame, the moment resting frame is basically going to behave in a shear mode, right. It is going to act like this. If you have a shear wall, then it is going to act in a bending mode. Now, when I combine these two things, it becomes a coupled frame wall building, and that is going to give me much more lateral load resistance, much more efficient structural system. So, typically they are connected by together, this. Now, how do you connect the frame and shear walls together? You need to have a good diaphragms. Diaphragms are the floor elements which are having thick slabs or a good topping slab that is going to connect all of them together, so that it is going to act as a one unit. Now, if you look at this shear wall component, if I am trying to create a shear wall action like this, I have number of walls, okay, through connections. These are all individual walls, let us say. Now, for the applied lateral load, when it has to bend like a cantilever, now at these interfaces I am going to develop lot of shear stresses. So, these joints have to be designed very in a careful way. So that's the reason between the walls I need to have connections that to be designed very well to make sure that these shear stresses are transferred effectively, so that all the wall panels which are cast individually and they are erected are going to behave as a one single unit. So let's look at it, how do we achieve that. For example, this is what we see here. For this kind of a wind pressure, for example, if you have a monolithic concrete, the shear stiffness is going to be very high. Now, when you have these individual wall panels like this, when they are acting together, the shear stiffness is going to be, it can be from 0 to infinity depending upon how you design it, right. So, if the shear stiffness, but still they are going to act, for example, let us say together, if you develop this interface reasonably well, then all of them are going to act reasonably well together, and then you are not going to have much slip or discontinuity in their deformations. But however, if you look at this location, if all three of them are going to act individually, if there is no shear is going to be transferred, then here in this case shear stiffness at the joint is going to be 0. So, all of them are going to act individually, which is the least efficient form of load transfer that you can have. So, we want to achieve this monolithic action that what we have in a typical cast in place shear wall, right. So, even though we are doing precasting, we want to make sure that all the precast wall panels are going to act as a one unit. That can happen only if I am able to develop at this interface very good shear stresses, right. Now, this is how, for example, if I take a monolithic concrete wall which is subjected to, let us say, the lateral pressure like this, horizontal pressure, and you will find that this entire thing is, you imagine this like a cantilever beam which is subjected to uniformly distributed load, right. So, what you will find here is, if I take a cross section, for example, that what you see here, in this cross section, that what you see here, you will find that the shear stresses are going to be like this, the distribution is going to be like this, and your bending moment distribution is going to be like this, just like your cantilever beam. So, nothing critical. So, I have a shear and I have a bending moment. These are going to be shear stresses, these are going to be my bending stresses, right. Now, if I look at this joint section along this line, you will find that the shear stresses are going to be like this. Right. Now, this is for a monolithic concrete shear wall, and all of them are cast together as a single element. Now, how do I achieve the same action when I have, like say, this is 1, this is 2 and this is 3 walls are together? Now, you see here there is going to be some discontinuity here between the joints because they are all not cast together. So, you will find that the shear stresses are still going to be like this, there is going to be stress discontinuity here like this, and the bending also, but if you look at the overall pattern, they are somewhat equivalent only, but though you have stress discontinuity like this between each individual wall will have some stress discontinuity, but overall when you look at this pattern, it is going to be like similar to what you have for a monolithic concrete shear wall, right. So, when you have the third element, of course, this is the least performant. You can see the lot of all of them are deforming in an individual way, which we don't want. So, we want to make sure that all three of them are going to perform together as a one single unit. Now, how do we achieve that? If one is the connection between these individual panels have to be designed properly, right. Then another thing is, if I am going for a dual system, I need to have a very good diaphragm system, or the diaphragm has to be very rigid and they have to be very well connected with the lateral load resisting system, then only it will make the dual system to perform to its potential. So, typically thin and stiff floor that transmits in plane lateral forces between lateral, this is what we say, diaphragms are basically thin and stiff floor system that transmits in plane lateral forces between the vertical lateral load resisting system. So, this is what it helps in transferring the lateral load to different lateral load resisting system that you have placed at different locations. This is the one that is connecting or tying the whole structure together. Now, what are the forces in the floor diaphragm? Due to seismic, it can come from inertial forces when the building is vibrating due to ground acceleration. Then you develop inertial forces, and it helps to transfer the forces between the primary lateral load resisting system, and typically they are coupled depending upon the stiffness and deformation compatibility of different vertical lateral load resisting system. So, typically there is a shear wall or a mount resisting frame or a combination of them, right. So, for example, you see here these are all diaphragms. That is what it is connecting all the vertical lateral load resisting elements together. Now, how do we understand the behavior of the diaphragm? So, for example, we see here if you take a one single story and if you look at your nominal design story force, which is a total inertial inertial force is this FDN, then what we do is we divide them and we distribute it to be uniformly distributed along the length of the floor plate. So, like this, so we allow it to be distributed. Now, you see here you have interior frames that are there. In addition to that, you have exterior frames that are connecting like this, and this inertial force now will be reacted by these forces that are developed in this interior frame. So, basically you imagine this like a beam which is subjected to uniformly distributed load like this, and you have different supports like this, right. Now, we can look at the overall moment distribution, and we can look at the overall shear distribution, which will be like this. Then we can model them as a deep beam using strut and tie method, that what we have discussed in the previous module. So, for example, of course, in strut and tie we know that you have nodes, right. Then you need to have some tie element that is going to connect them. In addition to that, you also have strut element that is going like this. So, these are all struts, this is your tie, and these are your nodes that are connecting the struts and ties together. This is the way that internal forces are going to do. So, this is one way of modeling the diaphragm as a beam, particularly it will act like a deep beam because your L by H ratios will be low. So, they will act like a deep beam. Okay, so this is one example how strut and tie approach can be used to analyze the diaphragm. For example, you see here these are all some column locations, okay, or the nodes we can see, and you have these black elements are going to be modeled like a strut, and the yellow colors are tie elements, and the green color one that what we see here is a nodes which is connecting the different elements that are coming on that particular joint. And these are your inertial forces. Depending upon the forces that it is coming, then we can understand where to put your strut and tie. And also it depends upon your opening that you have, okay. Depending upon the opening that you have, again we can model this as a one strut. So, basically it is like a deep beam. So, basically you see here this is your strut, and these are the inertial forces that are acting like this. So, your strut will form like this, and then these are your strut locations, and then the struts, the inclined force from the strut has to be balanced by a tie. Accordingly, you have to place your ties, right. Now, when the inertial force is on the other direction, it will exactly be you will form this kind of a strut and tie mechanisms, right. So, you can use your strut and tie method to basically model how you can design for your inertial forces.